Swayam Prabha. Digital India. Educated India.
The positive feedback systems are, we can define it as exponential growth equation. Let us try to compute that. So, the initial system we started with is ds by dt is g into s, that is what we start with. So, let us just into g, integrate both sides. Okay, steps. Let's do that. S at time 0 to S at time t, t naught to t, g into dt. If integral of 1 by s is logarithm of s. So, s at time t, s at time 0 equal to g into t. Which means that I can raise it to the power e and I solve it, then I can get s at time t is s at time s naught into e power gt. Right. So, then just raised it to power exponential and then moved the denominator to the right side. So, I get a stock at time t is nothing but initial value of stock into e power gt, and as you can see, these are positive values, g is greater than 0. So, g is greater than 0, then it is going to exhibit exponential growth just by defined by this term here. And of course, s naught is a constant value, I am just multiplying by a constant. And given the initial value of stock, and if I know g, and for whatever value of t, of course, I can directly compute what is going to be the stock value at time t. So, this is the value of stock at time t. This is your initial value of stock. Of course, if you want to get any different point in time, you just take that as the initial value and then take the time difference. That is denoted as equation 1. Bad thing about putting these things, it means that there are going to be more equations coming. Let us say this is 1. Okay. Now, let us see what can I look at. Okay, let me introduce this one. You can remember this, s at time t is s naught into e power gt. It is not that we always use this fractional growth rate of g, we also define something called as a time constant. Let us define it as capital T, which is nothing but a reciprocal of the fractional growth rate. Fractional growth rate g, that is T is just defined as 1 over g. Of course, since the time units of the units of g is 1 over time, so capital T's units is of course time. Where it is useful is, it is not that wherever we are looking at interest rates, sometime it could be the delay. So, instead of multiplying g by with the stock value, you can take stock divided by time value, it means the same thing. So, the equations stock at time t is equal to S naught into e power gt. Instead of g, I can always use 1 by t, 1 by capital T. So suppose an interval of time capital T passes from 1. So stock at capital T time will be stock at time 0 into e power gt is S naught into e power g itself is 1 by capital T. Capital T time units passes, so small t is also capital T. So that means S at time t is just S naught into e power 1, which is about 2.72 into S naught. So after passage of one time constant, the stock value will be approximately 2.72 times the initial value of stock. And if say 2 time unit, 2 t time passes, if 1 t time passes 2.72, if 2 t time units pass, then stock value will be 2.72 into 2.72 times, that will be the stock at time 2t. So this is defined as the time constant. Now let us come to our one question that we asked, what is the doubling time? Let us see whether we can compute that. Let us look at doubling time. Let us say Td, doubling time. It is a time after which, after time Td, stock value doubles. We need to compute this Td. Let us see. So 1 states that S at time t is S naught into e power gt. So I know the stock value doubles. So let us say 2 into S naught is equal to S naught into e power g times Td. Already have it. I am cancelling S naught and taking the logarithm on both sides, g into Td, which means that Td is equal to 0.69 divided by g, or 0.69 into time constant capital T. So this 0.69 will keep appearing because linear systems, and we are looking at even goal seeking, etc. Or they for computation or thumb rule purposes, people sometimes refer to it as 70% rule, that after with every dt time units 70% is nothing but 0.7 times your time constant, or nothing but roughly 0.69 divided by g. So for example, in our interest rate example, Td is 0.69 divided by 0.15, g is 0.15, which is about 4.6. Since our time resolution was, time interval of integration was 1, so only in the 5th period we were able to observe that it has double the value. If you had used a smaller time step, then you would have observed more closer to 4.5, 4.6. This is, so every 4.6 years or 5 periods, or it is just 5 years. So every 4.6 years, the value of stock is going to keep doubling. So, and that can be computed just by given the g values. So, if we know what is the fractional growth rate, then all we have to do is 0.7 by this for approximate value, 0.69 by 0.15, 4.6 in this case. Here is the doubling time. Yeah. So, there is nothing much to do with exponential systems other than just calculating okay, what is going to be doubling time and identifying it. So now let's go back to our slides. So we have seen this, we have seen the time constant. For passage of one time constant, stock value will be 2.72 times the initial value. Larger t or smaller g produces flatter growth curve. So now that we know all these equations, it's very easy to compute. That is not the intent. As we are looking at a more modeling course, we need to understand what will happen when based on the values of g. If you have a large value of g, then the growth going to be steeper. If it is a smaller value of g, growth is going to be more flatter. That is going to be much more time before you actually perceive the exponential growth. Doubling time, time interval required for an exponentially growing variable to double in its value. TD is 0.69 times your time constant. So now if we start plotting the level and the rate, that is, you plot the rate for every value of the level that we just saw for the example, for same example, you will find a linear line with the slope of g. It can be expected because it's just a linear equation, right. So for any positive value of g, you will still produce exponential growth. So even if this curve, even if this line is like this, I am going to still produce exponential growth, or the line is going to be like this, because I am going to produce exponential growth. We call these linear systems, coming from this diagram right here, where you can see that this line itself is linear, which is why the entire system becomes a linear system right there. Any questions so far? Not yet fully awake. Okay. Now let's go back and spend some time on looking at some graphs. The time horizon over which exponential growth occurs alters the perception of growth, even though the underlying system remains the same. So it depends on how much data that we want to look at from the past, or the time series data we are looking at, alters our perception. So let's see what we mean by that, and let us relate it with our variables of TD or time constant T. Let's see. Suppose the time horizons taken happens to be just 0.1 times your doubling time, then it looks like there is absolutely no growth. It's very easy to just dismiss, saying no, system is fine, it is just flat, there is no growth in the system, it looks very flat. This time horizon is just 0.1 times your doubling time. Your time horizon is 1 into doubling time. If you maybe if you squint your eyes or something, then you may kind of start to perceive some exponential growth, but for practical purpose it looks like a linear growth. It just goes from whatever in this example as 1 to 2 in the time constant, so it looks like a linear growth to us. So you don't start to perceive exponential growth at all, even if you observe system only until its doubling time, right. Doubling time is depends on 0.69 by g. So if g is going to be very small, then I am going to get a much longer doubling time. Suppose it's 10 times your TD, then you can start to perceive some exponential growth, which is shown here. But even then, observe what is happening in the x-axis. X-axis also changes with that time horizon, 0 to 10, then 0 to 100 time units, now 0 to 1000 time units when you start to perceive it. But the difficulty comes in is when you look at data from say 0 to 400, it is almost invisible to us, and it seems to say that nothing is affecting the system there, and suddenly things are active only after time 400, which is not the case. Underlying system is the same. But if you again take too much data, then you don't see anything, you just see that something is just spiking all of a sudden. That's an exponential growth. What is super exponential growth? Many positive feedback systems are characterized with doubling time that decrease rather than remain fixed as the value a system level increases. If doubling time is constant, that means you are having an exponential growth. After every 5 time unit passes, your level value, the stock value became 100, then 200, then 400, then 800. After every 5 years, the doubling time is constant. But systems such as, unfortunately, population systems, the doubling time is not constant. The doubling time keeps reducing far as the time it took, take 5 years to reach the double the value. Next time it may take just 4 years to double in its value, and following time it may take just 3.5 years to double in its value. So, as doubling time reduces, that means the value of G is increasing. That is what it means. So, if you plot as the stock value increases, the value of G changes. So, if you want to plot it from world population, you get a start looking at a non-linear system, because value of G is also now getting affected by some other factors. It is no more a external variable as we assume. As long as G is constant, does not change, then you got a linear system as well as a exponential growth. So, system is linear, growth is exponential. But if G itself starts to increase as we go along, as the stock level increases, then you start to get an what we call as a non-linear system, because the level and rate relation now became non-linear and the growth is going to be more pronounced. Look at world population example. If you assume exponential growth, then probably you will get the blue line. Super exponential growth, you are going to get this black line that you see here. Suddenly exponential growth does not seem so bad. You may be happy to have exponential growth. Then exponential growth is bad, then super exponential growth is so you want to move to exponential growth, then come to a goal seeking kind of systems.